Okay, today what we will do is we will use Hamilton's principle to derive the equation of motion for a very simplified problem. We call it application of Hamilton's principle. Okay, but what we will do is we will formulate the equations for a beam like structure under bending deformation. Then we will use the same principle equations for again a torsion problem. That way you have bending torsion of beam like structure derived, which we will be using it for the later aeroelastic analysis. Okay. Now let us take the wing is represented by a beam. I have not put it as a cantilever beam or anything like that. Okay. You can have different situations, like I can say you can put a heavy mass, which is the fuselage mass. I can call it, I am not going to call it M left, I am only putting left, the mass which is attached to the left side of the beam. And the beam, I define my coordinate system, this is my x, this is my z direction, and the mass per unit length, I call it lowercase m. This is mass per unit length of this beam. See, this can be fuselage mass. You follow? I can have another beam drawn this side. Then this may be in the middle of the beam. I can have half of it. Okay. And then EI, that is the bending stiffness. Okay. These are the quantities which are defined for my beam. So this beam is basically my wing, but they are functions of x. So it can vary along the length of the beam. And we define W, which is a function of x comma t, is the bending deformation. W x comma t is bending deformation, and please note m, ei, they are all functions of x, so they need not be constant. So if you want, you can even put like this. Okay. So for this beam, you have to write the kinetic energy, potential energy or strain energy, and then the distributed load. If you take the distributed load, we can define that by some C of, this is my external load which is acting on the wing. Okay. Now let us write the kinetic energy expression. Now kinetic energy T is the length, we take it as L, the length of, so you will have 0 to L half m W dot square d plus I have to add the, why I have included this is to indicate what will be the effect. I can have put one more also on this side, okay. It does not matter, I can have any condition, because I am just describing for one situation, then for different situation you can derive things by yourself. Plus half m left w dot at 0, okay. The dot is d by dt. So when I have this definition, that means d over dt square. There is no integration for this, because this is a heavy mass which is acting at the left side, okay. Then you can have strain energy, which is again 0 to L, half. For bending strain energy you have EI, bending moment, and curvature. So you will have del W dx, because this is the curvature expression. And you have external load that we will include it later. Right now what we have to do is apply Hamilton's principle. Says integral delta t minus delta v plus delta T2. So what we will do is we will evaluate each quantity, okay, term by term, because otherwise the board is not sufficient for me to fill up. So what we will do is we will evaluate first the variation of kinetic energy expression, we will write it. Then we will write the variation of strain energy expression and then write it. Later we will write the variation of external work, right. Then we will combine all of them and then get the final expression, okay. So I erase this part. We will take first the kinetic energy expression. The kinetic energy expression you will have integral T1 to T2 delta T dt, which is I have to take the variation of T here. The variation is T1 to T2 m w dot delta w dot dx, and this will remain as it is, plus you will have that other term m left w dot at 0 delta into, because you need to have one more integral here, please understand. Yes. This integral is 0 to L, and then I will put a bracket here. Okay. So the inner integral is over dx, outer integral over dt. What I will do is, for the, because this is the first term, I will switch the order of the integration and then integrate first with respect to T1 to T2 and then keep the integral 0 to L outside for this term. This term is not an integral, this is directly only T1 to T2, okay, with dt. So let us write first this part. If I integrate by parts means what I will do is delta w dot is nothing but, if I will write it, delta w dot is delta of delta w by delta t, which I am writing it as delta by delta t of delta W. Because W is a function of x and t. That's why I put a partial derivative. Now what you can do is this into dt I can integrate by part. So I do integration by parts. I will write here 0 to L m w dot del w in the limit t1 to t2. You will have a dx here. I can put, because this is t1 to t2. This integral is t1 to t2. I have a dx also. Minus integral 0 to L integral t1 to t2 m w double dot delta w dt dx. Okay. And then this is for the first term. Second, I will again do integration by parts. If I do that, that will be plus ml double dot w dot 0 delta w at 0, that is at t1 to t2, minus integral t1 to t2 ml w double dot at 0 delta w at 0 dt. Okay. Now this integral is over the space, but this delta w is over the time, initial time, final time. Okay. And what we say is we said that the initial time and the final time, the variation is 0 in our Hamilton's thing. Therefore, this term same is the case with, because this is variation in the initial time at location 0. This 0 is the starting point, x is 0. So final time also that is. So these two integrals, these two terms will become 0, leaving behind only these two terms. Okay. That means whatever I have written delta t dt, it is. Now I can erase this part and write it in very short form, and that becomes much simpler for me in so I erase this part and then put it as, because later it will be easy for me to substitute, minus integral, here now I have changed t1 to t2 integral 0 to L m w double dot delta w dt dx, and then minus integral t1 to t2 ml w double dot at 0. 0 is the 0, not time, 0 location, delta w. If you want to put, you can put a comma t, w double dot comma, here you can put comma t. Okay. Next what we do is we have to take the variation of strain energy expression. Strain energy expression, if I take here again t1 to t2 delta V dt T2 0 to L EI del square W by delta R. Okay. And as usual, again I will take the variation and this differential, because this is what we call it as a weak variation. Variation of the curvature of the variation. You can interchange both, because that's why the variation is a weak variation. Small you vary, don't put a large. It's a very subtle. It's not that one differential you can just flip. Variation is different from derivative. Okay. Now this expression again you integrate by parts, because I will be taking this inside and this derivative I will take it outside. Then I will have dx. I can integrate by parts twice. Actually, first time we will integrate. This will be essentially T1 to T2 EI. This is del square W over delta x square delta of delta W by delta x. You can write it, because this you can take it inside or outside, doesn't matter, minus integral here there is a 0 to L, because please understand this integral I am doing it over space. Here I did partial differential, I did it over time. Here I am doing that partial integration by parts, I am doing it over space. Here I will have 0 to L, so you can put it bracket here, delta by delta x of EI okay dx dt. This is the first. Then again I will go and do the integration by parts to the second term, because this d over dt d over dx del w is there. Okay, so this will be, I will write it T1 to T2. This term will remain as it is, EI del square W over delta x square delta of delta W delta x 0 to L minus, I will have, this is integration by parts again. This will be delta over delta x of EI del square W by delta x square delta W 0 to L, and again minus and minus, this will become plus integral 0 to L del square by delta x square EI del square W by delta x square delta W dx, and then you have dt, because this bracket. Okay. So now you have three terms here, and you got here one term delta t, this is delta v, and you have to write delta we. Delta we is fairly straightforward term, which is integral 0 to L, because we said the loading does not change during the virtual displacement. This is delta W dx, and you have T1 to T2, this is dt, this is delta WE integral T1 to T2 dt. This is this expression. Okay. Now what you have to do is, you have to combine all the terms, and when you combine, I will write the full expression so that it becomes clear. Okay. So what is my first, maybe I will start from here, that way it is easy for you to write it. Please understand, I have to start from delta t dt. That term is minus integral 0 to T1 integral 0 to L m double dot delta W. Okay, this is the one. Then I have this expression minus integral T1 to T2 ml W double dot, this is 0 then I have to add this. Add means I have to subtract. Okay. When I subtract integral T1 to T2, sorry, yeah, okay. Now I need to take this term, put it here along with this. What I am going to do is, because the T1 to T2 is here, I will again write T1 to T2 EI del square W by delta x square delta of delta W by delta x 0 to L, and this integral is over dt. So I am having dt here, only dt, and the second term, this minus and this will become plus. So I will have plus delta by delta x. You can have an integral also, T1 to T2 EI del square W by delta x square delta W again 0 to L dt. Okay. Now this term, if you look at it, this has a T1 to T2, okay, T1 to T2 0 to L, and so I am going to add that only here directly. I will put it just below expression, that will become a minus sign. So I am putting a minus integral 0 to L del square by delta x square EI del square W by delta W dx dt. Okay. And then the last term also has two integrals. So I am going to put that two integral also, that will be plus. So I am putting plus integral T1 to T2 integral 0 to L z x comma t delta W dx dt. This entire term is equal to 0. Okay. Because that is what the Hamilton's principle, because substituting all equal to 0. Okay. Now what we have to do is, we need to collect the terms and then write our equation. While collecting the terms, you see all of them have integral T1 to T2, 0 to L, T1 to T2, and you have okay, dx dt delta w. Delta w is common for all these terms. Now, delta w is a function of x and t, and this is a virtual displacement. Virtual displacement is arbitrary. So, along the whole 0 to L, that path you can have at a fixed time, you can have a variation. Then I can set the terms within the bracket of delta w equals 0, because this variation, you said right hand side is equal to 0, then you may ask what happens to these terms and this term, okay, because these are variation at a particular, what is the time, okay, this is because this is at location 0 at time T1 to T2. Here you will have again variation location 0 and T1 to T2, okay. So, you will find that these are only at specific points, whereas this is, I can vary over the entire domain, which means if everything has to be 0, the domain part independently must be 0, because I can have independent variation in delta w over the entire domain 0 to length L. Therefore, you write your equation, this is combining all, you will find minus m w double dot minus del square by delta x square ei del square w by delta x square, this is the second term, then plus x comma t, this is 0 independently. Okay. All right. In other words, this is valid everywhere. You always say 0 full in the whole domain, because delta w is arbitrary in the entire domain. So, this term is set equal to 0 in this. But now let us look at this, these terms, okay. This is a variation of w at location 0, that is the left end of our x is equal to 0. This is variation of my slope 0 or L, okay. That means these two are different, whereas this term, if you look at it, this is delta w, one of the term is at 0, another is at L, okay, which means these are over delta w, each one of them must independently be made equal to 0, okay. That is, let us take first this expression. This expression will have ei del square w by delta x square variation of delta w by delta x at either 0 and at L. This is Now the question is, you will specify what type of condition I am having. That is where it comes. This is very, very important. Now when you write this expression, this is again what will you have? You have plus delta by delta x of EI del square W by delta x square delta W. I am putting only first term L. Please understand, I am not putting, this is only at location L I am taking. Then location 0 I am writing separately. Location 0 will be minus delta x EI location 0 is also, this is location 0. Okay. So I will have minus M L W double dot. Okay. This is at location, this entire term. If you want, you can put a plus sign and make this whole thing as one term, and location 0. Okay. This is at location L, this is at location 0. All right. Now let us look at it a little bit carefully, what our original beam is and how we obtain these boundary conditions, because that is the key to the entire problem. This is my field equation. Okay. I will write my field equation, which I always specify as field. This is, I can write del square by delta x square EI x square plus M double dot. If I want to represent it in partial, it is, some books they will write it delta W by delta T square equals Z x comma T. This is my field equation. Now you go to the boundary condition. Okay. For the given problem, the given problem was we put a large mass M left side and then we had the beam. Okay. I have not restricted the motion at the left end, which means I allow the motion. If I have that motion, slope, I am not restricting the slope either. I am having displacement, I am having slope at the left end, I am having displacement and slope at the right end also, which means only this quantity is, I can have a variation. That means what should be 0 is EI del square W by delta x square at 0 equals 0, as well as EI del square W by delta x square at L equals 0, because L also can have, this is a free end, this is also free, I have not restricted anything. Okay. Now let us come to this particular term. here, is there a, did I miss one term here, delta W? There must be one term I missed here. I think delta W I have to put, right? Yeah. Maybe I will write that delta, I have to put a, okay. Now let us look at, this is at L. L means that is this end. At this end, my delta W, that is free. I can have a variation in that case. That means only this term has to be 0, which is del over del x of EI del square W over delta x square at L is 0. Okay. Now let us come to this. Left hand side, delta W, this is a 0 condition, it is free. It is free to move. That means this term must be equal to 0, which is, I am going to put minus delta over delta x EI minus M W double dot at 0, at the 0 location. Okay. Now these are 1, 2, 3, 4. My 4 boundary conditions. So I call them this as boundary conditions. Okay. Please understand one thing. Here I want to emphasize that the field equation, that is this equation, will be same even if I change my boundary condition. Suppose for the sake of explanation, I am saying I have made it into fixed. There is no ML. Now, that means my ML is gone. Now this is a fixed boundary condition. Fixed boundary condition, when I go, I will first start with here. At the 0, because this is at L, this is free. So I can have any slope. That means this must be satisfied at L. But at 0, whether this is the condition or some other condition, at 0 you know that you are not allowing the motion and it is actually cantilever. So you don't allow rotation. That means you will say slope is 0. Instead of this condition, bending moment is 0. You understand? So your entire condition will change. Slope is 0 here, and at this point curvature is 0. When you come to this point, anyway, right hand end, it is the same, shear force is 0. But when you go here, you will not apply this because ML is not there, so you don't put, you will look at delta W. I don't allow displacement. So for a cantilever beam, my boundary condition will completely change. So I will write that boundary condition for just for clarity only. Okay. So you find, depending on the problem, the boundary conditions will completely change. If it is a free beam, you will have another boundary condition. I can put a spring here, it will have another boundary condition. You follow? So depending on the situation, if it is simply supported, I will have another, because there simply supported means I don't allow displacement but I allow rotation. okay, you will have another boundary condition. So the interesting part is for a cantilever beam, boundary conditions, that will become displacement with 0, that is W at 0 is 0, delta W by delta X at 0 is 0, the slope is 0. I have put restricted, and then you will have EI del square W by delta X square at L, this is 0, and delta over delta X of EI del square W by delta X square at L 0. So you see, these are the boundary conditions for a cantilever beam. These are the boundary conditions for a beam with the okay. This is one, this is another. Like that you can have free beam. Free beam, once you leave it, you are not restricting. That means the same condition will come on the left side. You understand? Bending moment is 0, shear is 0. Now the solution to the problem, that is where the next step is, because you obtained the equation. Please understand, Hamilton's principle will give you the equation which is valid for the field, and the beauty of this is it also gives you boundary conditions. Boundary conditions for the given problem. Why I choose this M here is one mass at one of the ends, I put it, because later when I derive very general principle for solution of this type of problems, if I put everything 0, 0, you will find that I will not be able to bring out a generality. Whereas if I put a mass at any end, left end, right end, anywhere, I can give a general expression for one formulation. How do you get the solution for that? Because this is where these are, you can call it the boundary value problems, but these are partial differential equations. Please understand, this is a partial differential equation, space and time, and then how do you go for solution? This is where we've learned how to solve, and these are operators, because these are differential operators. We will first do some separation of variables, convert this problem into one ordinary differential equation. First understand, these are all PDEs. That is why when you derive with Hamilton's principle without doing any approximation, later we will use the Hamilton's principle, but you will get the ordinary differential equation. That is another way of deriving it, but that part I will teach later, next. So you understand how do you get the equation of motion along with boundary conditions. That is very, very essential for our aeroelastic problem. First, what is the equation of motion? Because in this structural equation, because please understand, this has the structural part, this also has the inertia part. Okay. Now, this is the only part which we do not know as on today, in the sense, this is the external loading part, which is the aerodynamics part. That part we will derive separately. First, we assume that that is somehow known. How do we get the equation of motion, number one, and what are the various solution methods? Because please understand, you cannot get a solution for this problem exactly, because exact solutions are available only for very few special cases. You cannot get exact solution for all this, any kind of problem. Okay, that is why you need to learn approximate methods of obtaining the solution of the equation. Okay, now you want to, oh, wait a minute, I will erase this part. then we can start. Okay, now we will derive the equation of motion for a torsional vibration of a beam. Okay. Here again we can, that's why I said any boundary condition, you first, when you describe the problem itself, that comes what type of boundary you are having. I can put a mass here with an inertia. Okay. Let us consider a beam of length L, and this is acted on by, this is my motion I am describing, torsional motion, twist, and there is a distributed moment which I call it M. So this is my X. Please note here I am using the symbol M for moment, not for mass. Okay. This is a distributed twisting moment. Okay. And then I will write IP, which is mass moment of inertia per unit length. I is mass moment of inertia per unit length. All are per unit length also. This is the distributed moment. And then I need to have, similar to bending stiffness, I have a stiffness. Torsional stiffness is, you call it GJ. GJ, which is also can be a function of X, torsional stiffness. Okay. Now again you go back and then apply Hamilton's principle. You need to write the kinetic energy, you need to write the strain energy, and you need to write the work done by the external moment. So your kinetic energy expression T will be L half IP dx. Okay, and your strain energy half GJ delta P over delta X whole square. Okay. This is my Saint-Venant's torsion problem. I write my strain energy in this fashion. Okay. That is why all these things are initially understood. What is the kind of Saint-Venant's torsion? Please understand J is torsion constant, because we are dealing with aerofoils. Okay, aerofoil are not circular sections. So J is defined as a torsion constant. It is not that polar moment or something like that. No, don't have that confusion at all. That's why we write Gj is the torsion constant. Torsion stiffness. J is the torsion constant for the given cross section. Now, if you are given a single cell box beam, if it is a box beam, because my aerofoil, I can put this, define it like a box beam, single cell or multi cell. Okay, please understand. I can do it like this. I have to get the torsion constant for this type of section, multi cell box beams. This is what you must have learned in structures 1 course. If you have not learned, you better go back and then learn that. For simple problems, you can take a single cell box beam. Okay. Then you say as though the entire wing is only a thin walled. Okay. Thin walled. Thin walled. Only one cell. For that you can apply the Fred-Batho equations and get the torsion constant. This you have to know, because how do you get the torsion constant is, you should know that. Okay. Now let us apply the Hamilton's principle. So first is we will write integral delta t dt t1 t2. I will substitute here, this will become T1 T2 0 to L IP P dot delta P dot dx dt. Okay. Now I integrate by parts again. If I integrate by parts, it will become 0 to L IP P dot delta P T1 T2, there is a dx here. Okay. Then minus integral T1 T2 0 to L IP, this will become P double dot delta phi dx dt. Okay. Maybe I erase this part, not necessary. Okay. Or let it be there, no problem. Okay. You have obtained for the delta t. Similarly, you go and write for delta v. You will have T1 to T2 delta v dt is T1 to T2 Gj delta phi by delta x into delta of delta phi by dx dt. Okay. Again you integrate by parts. Now with respect to space, then you will get the equation integral T1 to T2 Gj delta phi over delta x delta phi 0 to L, and there is a dt you will be sitting here, then minus integral T1 to T2 integral 0 to L delta over delta x of Gj delta phi over delta x delta phi dx dt. Okay. Now as usual, I will erase this part. The external twisting moment, that delta We will be just mx del phi. That's all. So that that you will write it as this will be T1 to T2 okay. Now you combine this term and this term. Okay. Combine all the three with proper sign convention, then you will have the field equation will be P double dot plus delta over delta x of Gj delta phi over delta x, okay, because the first term is minus Ip phi double dot, that is a minus sign, and then T minus V. So the minus and minus plus mx, this is 0. This is my field equation. Okay. And then boundary condition you go. You know that here anyway T1, T2 initial del phi has to go to 0, therefore this term is out automatically, T1 to T2. Whereas when you come here, the boundary condition for the given problem, we said that the left end is fixed. Fixed means at 0 I don't allow any variation in the displacement. Therefore phi is 0 at the left end. So phi at 0 is 0. But when I go to the right side, that is the length L, at this point it is a free end. That means what is 0 must be this term, which is actually Gj delta phi over delta x at L equals 0. Okay. That means this is the fixed end, this is the okay. Suppose if you put a mass, that's what I am saying, you put some disk or something like that at that end, that will have its own inertia, that kinetic energy. Then that kinetic energy expression will come here. Then that will come as a boundary condition. Okay. So you will find that depending on what you put where, the boundary condition will change. Suppose you say, I am just going a little further. You may have some problem like this. In an aircraft, old aircraft, you are supporting by some structure here, somewhere in the middle. Okay. Then how will you model this? See, all these problems you have to pick, because you are modeling. Today everything is a cantilever beam, all the wing structure. In the old days they put a strut and then attach it. That means there are two ways. One is you can break it into two parts of the beam and then match the boundary condition there, this. Or you can say this is like a delta function, which is an external load which acts at that point, additional external load. Today you know that most of the aircraft, they carry a engine. Maybe it doesn't hang down. Engine is here. Engine is mounted on the wing, and that mass is sitting there at a concentrated mass at some particular location. How will you treat that into account? Okay. There are two ways of doing it. One is you put it in the kinetic energy expression. Use it as a delta function in your m. See, please understand here, this m is mass per unit length, it is going. But there is another heavy mass which is sitting at some particular location. What happens is at that location suddenly. So either you can put it like a delta function into that whole problem, or you may have to split the beam into two parts, okay, then put one end that mass, another end you start at a free. So the problem gets a little complicated. You can't solve that so easily, depending on you put various things at. Now this is where you learn the approximate methods, because you cannot get a very close form solution. Suppose if you have a beam which is supported at several locations, that is a multiple supports. You can apply that piecewise, these equations, substitute the suitable boundary condition at every point. Okay, that is where the problem is very, very important. How you formulate your entire equation of motion and the boundary condition. Okay, we have taken only, because why I did bending and torsion, because we need that, because the wing can bend, wing can twist. So that is why bending torsion problem we have developed it. Now the interesting part, some of the interesting thing between these set of equations, if you see here the order of the equation, order in space derivative. Time derivative is always inertia, that is the second derivative. Space derivative here is 2, second order. Whereas in the bending problem, the order of the derivative is 4. Okay. So you are having a higher order problem. Now, if we want to get a solution for a general, because we are going to describe all these problems in a general fashion. How do we do it? So that all of them are brought under one category of problems. Okay. So for really analyzing these problems, because please understand, I have an external loading which is sitting here. Moment, there I have, if you say lift, that lift is there, this is the moment on the wing. Both are sitting at the problem. But how do I solve this entire problem? Because I have a time derivative also. Suppose if it is a static problem, only wing deformation under a load, I am not bothered about the vibration. That means this is gone. And there also, this is what you had your beam bending equation, bending of beam static equation is, this is that of HT. This term is 0. So you find Hamilton principle gives you even the static problem, along with boundary conditions. Only thing is, all the partial will become total derivative, because there is no time variation brought in the problem. Okay. Now the question is, if you have time, because static problem, I taught you one, you have learned that part, Rayleigh-Ritz method of obtaining approximate solution, because you cannot get solution for any EI variation, because please remember here EI is a function of x. Similarly, Gj can be a function of x. So when you want to solve static aeroelastic problem, that is one set. That means time derivative gone, you solve the ordinary differential equation. Okay. Whereas when you go to vibration problems, these are partial differential equations. So what we do first is, we do free vibration problem first. What are the free vibration characteristics of beam in bending and torsion? Okay, that is the first step. And then using that solution, please understand, using that particular solution, you convert them into ordinary sum. Actually, when you do separation of variable in the free vibration, you do it, and after that convert it into ODEs, ordinary differential equations. Now that is where you get a free vibration problem. First you have a partial differential equation, this partial differential equation you convert them into ODE, and then the ODE is, now you have to know how to solve that ODE. You follow? And then, because that is not your only aim, because you need to find out what will happen to the beam when you have an external load also. Then that is a response problem. But for studying the response, you need to first know what is the free vibration characteristics of your wing or your entire aircraft. Okay, because that is essential to get to the response problem. So you need to study how do you get the free vibration solution, and that is where the first PDE is converted into a ODE. Okay. Then comes, I told you what type of operators, that Sturm-Liouville theorem, what it says. If the equation is of this form, okay, you will have solutions of this type. You understand? And that is where that equation is applicable. But that is derived for only second order systems. But you will find that also, so that application, if you see boundary value problem, any book, differential equations and boundary value problems, they will deal with that. You can solve, they will give a solution for second order, but you will also apply to fourth order. There are several conditions, orthogonality of the functions, etc. Those are generally proven for a most general problem. They will not be very specific to bending problem or specific to torsion problem. That is why what we will do is next class, we will have a general problem and then write the equations. You will have an idea of how those are written. Okay. So first I will just briefly give you one introduction to that. See, let us take this equation, free vibration. Free vibration means I don't have this. So free vibration of a bending problem. Because I just want to indicate one thing and then free vibration of a beam. Okay. You write it, z of xt is 0. So I will have my equation EI del square W plus M is 0. Of course, boundary conditions we will keep them at there. Later we will substitute that. First I am going to assume that my W, which is a function of x comma t, I can write it as something like this. This is what separation of variable. Okay, I am writing as a assumed solution. I will go and substitute here. Okay. When I substitute in this place, what will happen? This is all partial. Now this is only a function of x, that is a function of t. So I will have this term qt into, I will have d square by dx square, please understand, into EI d square capital plus, here I will have, because this is a, so I will put M Q double dot W of x 0. Okay. Now what I do is I take this term to the right hand side and then collect all the space dependent terms on one side and then time dependent term on the other side. Okay, if I do that, I write it here itself so that it is easy. So I am now collecting, I keep this term, I will divide by Wx. I take double dot, that I will take it separately. So you will have d square by dx square ei d square w by d. Okay, you can put equals. I am dividing by m, because please note why I am taking m here. M is also a function of x. Okay, that's why I brought it here, and I will put this as minus q double dot over q. Okay, now you see this is totally space, this is totally time. If these two are equal to each other, it should be equal to some constant. So I will write constant, and I am going to use it as the constant, as I am going to put lambda, constant lambda. Okay. Now you know that I look at only this equation. Please understand, I am looking at this part of the equation. It says that minus q double dot equals now I can bring it this side. This is a second order differential equation in time. So this equation is q double dot plus lambda q equals 0. Okay. Now this will have solution. Suppose you have to see whether lambda should be positive or lambda can be negative. Okay. Suppose, or what should be the nature of lambda? That is the key. Okay. This comes from physics. You can always write q equal to some q bar e power st. Okay. Then your characteristic equation will be s square plus lambda equals 0. So you will have characteristic equation s square plus lambda equals 0, or s is equal to, this is going minus, what is that, minus lambda under root. So you can put it two roots, s1 comma 2 is plus minus. Okay. Now if lambda is positive, then it is an imaginary number. That means my roots are imaginary. Imaginary roots means s will be I plus minus I, which you can write it as sine and cosine function, which are oscillatory functions. On the other hand, if lambda is negative, then what will happen? Negative and negative, this will become positive. Then positive under root, you will have one of the positive roots, one negative root. That positive root, what will happen? It will take increase with time. That means what? Your solution is going to blow up. But nature in beam or anything is nothing, it just vibrates. Therefore you say my lambda has to be a positive constant. Okay. That is the reason we will now write, instead of writing lambda, this is the proof. Normally this is given, because what should be the lambda? Positive, negative, etc. So we always say, instead of writing lambda, we will put it as omega square, because square is always positive. So q by q dot. Now you will write your equation. Okay, this is my a sine omega t, etc. b cosine omega t. This is a harmonic function, time varying, excellent solution. But the next question comes, what should be my omega? You say that this is a positive number. What should be my omega? Whether it is valid for all omegas, because positive number means you can have any number. What is the condition? Okay. That particular solving for those omega which satisfy my problem, that is called the differential eigenvalue problem, because you are now going into this side. You will go this side because I know this is equal to omega square. Okay. That is your differential eigenvalue problem. I can write it as d square by dx square ei d square w of x over d square, dx square, right, equals m omega square This is my field. This is purely a ordinary differential equation in space. Now let us look at the boundary condition. We will go here. We have to again substitute W, because we know that at root equal to 0 moment. So Q of t, that is the time varying function, that will go off. So you will have ei d square W by dx square W, because these are all space derivative only. This is also space. So wherever you will have capital W, capital W. When you come here, you will have space, there is a W double dot. Okay, here you will have, what is it, omega square, because you have to differentiate, because time derivative comes, Q double dot will be there, but the Q double dot is going to be omega square, what is it, minus omega square Q. So what will happen, that omega square term is also sitting in boundary condition. That is why I use this particular example to indicate this omega square can be, it is in the equation, field equation, it is here. It can also sit in the boundary condition. Okay. Whereas in these boundary conditions it is not sitting, there is no omega square here. This boundary condition doesn't have, this doesn't have, this does not have. These are just homogeneous boundary conditions, directly equal to 0. There is no omega square sitting in. Okay. That is why the boundary conditions are also split into two types of boundary conditions. One, there is no omega square present. Another one, there is a omega square. Now these two are different. Please understand, because when you actually solve the problem, you have to that orthogonality principle, everything that has to come. Otherwise, several books will simply deal with only this part and rest of them zero. Okay? But some books explain that you have to take the omega square. That is why splitting the boundary condition into two parts. Okay? And this is what is, I will just generally mention the form of the equations. Okay? Please understand, this is, now this is not necessary. I will just write the equation. After that we can, I think this also I will erase. So you will write it as L W equals sum m omega square W. which these are all function of x, please understand. And then I will write bi 0, this is one type of thing. Another one is bi w equals some capital M or something. Okay. Oh, sorry, not W. Not. Okay. The Ci contains that mass. Okay. Why I have written is, this is, you can have these boundary conditions of this type, or omega square also can be sitting, but how many boundary conditions you will have as the, what is the order of the differential equation. That is why we always say this is 2p order, 2p, p can be 1, 2, if it is 2, that is a 4, if it is 1, second, that is what torsion problem. And you must have that many boundary conditions. Okay. So you can split it into this part. Okay, so boundary conditions are of this type, some boundary conditions are of this type. Okay, we can write it as, this is I running from 1 to k, and this is again I running from k plus 1 to p, but I will say at x equal to 0 and L, and at x equal to 0 and L. 2p, total 2p. Okay. This is how I write my differential. You can say this is a linear differential boundary value problem. That's all, of order 2p. That's the linear operator. This is a linear operator. You may call this as a differential boundary value problem. Or differential eigenvalue problem, boundary value problem, anything you can say, because that is the boundary value problem. Now you have converted into solving omega square. Okay. That's why you may call it as a differential. You may put it even eigenvalue problem. Okay. Eigenvalue problem. See, this is a general form. Now you need to analyze what is the type of operator L is. Okay, here it is a 4, and this is where adjoint operator, self-adjoint operator, all those things will come into the picture. Okay.